Hello, bonjour, it's Laura here. In this video, I'm going to talk about precipitation reactions, or reactions that take place in aqueous solutions. So, the first thing that you need to know about precipitation reactions is they are actually a double displacement reaction. So remember we talked about how in a double displacement reaction, elements switch places in a compound. So you start with two compounds, then you end with two different compounds. A precipitation reaction is that type of reaction. And the interesting thing about a precipitation reaction is you start with two ionic solutions, so two aqueous solutions where you've got ions floating around. And then you end with one that forms a solid. So you're actually forming a solid, and another word for solid is precipitate. So that's where the precipitate comes in the precipitation reaction name. So you can see in this picture here, we've got actually two ionic solutions. So this one's yellow, and it's being poured into this clear, colorless liquid in a beaker here. And then you can see you've got this cloudy yellow forming. This is actually the precipitate. So right here, that cloudy yellow stuff, that's the precipitate. And when you're looking at precipitation reactions, that's often how it'll look at first, is just kind of cloudy, and then that eventually settles to the bottom, and you can see that you actually do have a solid there. Now, before we talk too much about precipitation reactions, we want to understand what's going on behind the scenes. And to do that, you need to understand water, because remember, these are happening in an aqueous solution, which means they're happening in water. So remember, water has polar molecules in it. So, and we've talked about this before in organics. So if you look at water, the molecules, each one of these compounds here would be one water molecule. And remember, the oxygen is a partially negative area, so partially negative area, and then the hydrogens are partially positive. So the oxygen has a bigger pull on the electrons, so there's sharing going on of electrons, but not equal. So the oxygen's got a partial negative, and then you've got a partial positive area. So that's really important when it comes to dissolving salts in water. So I've got a picture here of a beaker. So this is a beaker of water. We've got a lot of salt at the bottom of this beaker, and actually what's going on is there's so much that it's not completely dissolved. So you've got dissolving happening right here. So the salt's actually being dissolved into the water. So this would be a close-up of that picture. So this lattice structure here, that would be the NaCl. And you can see that you've got positive and negative areas here. And the water molecules are coming in, and they're kind of attacking this. They're not attacking it, but they're coming in and being attracted and pulling these ions off. So the positive hydrogen area, that can be attracted to the negative chlorides in the salt. And then the same thing can happen over here. So the partially positive area of the oxygen, that can be attracted, or sorry, the partially negative area can be attracted to the positive sodiums of the sodium chloride, or the salt. So they actually pull them away from the solid. And then this is what it would look like if you could actually see it. So that positive sodium is surrounded, and it's all the negative oxygen surrounding or turning towards the sodium, and then you've got all of the positive hydrogens surrounding the negative chloride. So that's how it's dissolved. It's actually disappearing kind of into the water, because the water molecules can surround the positives and the negatives. So that becomes important when we start talking about soluble versus insoluble salts. So ionic compounds, they're basically salts. So whenever we talk about salt and ionic compound, they're basically the same thing. So we have ionic compounds that do dissolve in water, and you're really familiar with that. So for example, if you have a teaspoon of salt and you pour it into a glass of water and you stir it up, that salt's going to disappear. If you pour tons and tons in, more than the water can actually dissolve, you'll have some at the bottom, but you know that table salt is dissolvable in water. If something is dissolved in water, that means it is soluble. So this is an important word. Soluble means that it's dissolved. Okay, so now go on to ionic compounds that do not dissolve in water. So that means that they are insoluble. Okay, so these words get a little bit confusing. Insoluble, that actually means that it's going to be a solid in water. So here we've got a picture of two test tubes that have salts that are solid in water. They're actually not dissolved in the water. So we've got lead 2 iodide here, and then we've got nickel hydroxide, or nickel 2 hydroxide here. So you can see they've both got that cloudy structure. That is actually the salt, and it's a solid. So it's insoluble in water. Now, if we were showing a soluble salt in a chemical equation, we could write the ions or the compound, and then we would write AQ behind it. Oh, sorry, I'm having trouble with my pen there. So say I'm writing a chemical equation, I'd write NaClAQ. Say I was writing a chemical equation that had an insoluble salt in it. So say I had the lead 2 iodide. If I wrote that in a chemical equation, I'd actually put S behind it for solid. Okay, so that S means solid, not soluble. AQ means soluble. Okay, so those words and symbols are sometimes confusing for people, so just make sure that you've got that cleared in your head when you're writing these chemical equations. All right, so let's go on. Now, you probably are wondering, well, how do I know whether a salt is going to be soluble or insoluble, and how do I write it in a chemical equation? Well, we've got solubility rules that we can look at. So you'll find these in any different chemistry textbook or the chemistry handbook. This is the one that we can use in class. You can also find them on the internet if you want, and that's fine. What you want to do is practice using it as you're doing your homework so that you get used to how to read it. So the important thing with these solubility rules is it'll always tell you an ionic solid is soluble if it contains certain things, but then it's got exceptions. Okay, so you need to pay really close attention to the exceptions to the rules as well as to the rules. So what I want to do is go through a couple of examples. So I recommend that you pause, print this off, and then have this with you as we go through the next slide where we're practicing determining whether a salt is soluble or insoluble. Okay, so let's do that now. So in this first one, we'll do each of these separately. So we've got an ionic compound here. So this is potassium sulfide. So we want to know if this is going to be soluble in water or not. So what I'll do is I'm going to look at my solubility table here, okay, and I see that if it contains potassium, it's soluble. So soluble if it contains potassium, okay? And then there's no exceptions. So that means that this should be soluble. And I'll put the potassium ions are soluble. That's our reasoning. Let's go to the next one. So here we've got calcium nitrate. Okay, so let's look at our table here. We've got nitrate or nitrite right here. So that means if a salt contains nitrate, it's soluble and there's no exceptions. So that means this should be soluble. So I'll write nitrates are soluble as my reasoning. Now let's look at the next one. So here we've got lead chloride. Okay, so let's look at our table here and see if we've got any rules. So here you can see my finger on the chloride. So chlorides are going to be soluble, but look, there's exceptions here. So actually lead is an exception. So if you've got lead and chloride, that's an exception, and that actually means it's insoluble. So I'll put insoluble here. And then that's because lead is an exception to the rule. All right, let's look at the next one. So this one is sodium hydroxide. So we'll look at our rules here. Now, if I look at the very top again, sodium is soluble, and there's no exceptions. So that means that the sodium hydroxide will be a soluble salt. So that means it's dissolved, it's not a solid. Okay? Na are soluble. And then let's look at the last one here. So the last one is aluminum phosphate. All right, so let's look at that. So we've got here an exception. So phosphates are insoluble. Phosphate salts right here. So that means insoluble. And then I can write that the phosphates are insoluble. Okay, so you get the general idea of how to use your solubility rules chart. Now we've got a lot of textbook questions for you to do, a lot of learning checks for you to do, so make sure that you really practice with one chart and get used to using that one chart. You'll be able to have that on the test. Okay, well done, Miigwech.